So we're back to the second part of Lecture 7, okay, and we want to begin to understand the electric and the magnetic field in more detail. We've seen that the magnetic field is an implication of special relativity and static electric fields, and we've studied a lot of the geometries of interacting particles, okay, by using the Lorentz transformation between two frames, and we have the Lorentz force law. I illustrated it in part 1 of this this lecture series for a particular geometry, and then you generalize that to other geometries, general geometries, different velocities for the particle Q2 in the frame S in problem sets and in recitation section, and then you see that the Lorentz force law covers all cases. Now I remind you that the Lorentz force law reads this: that F is equal to Q of times E plus U cross B, where U is the velocity of the particle that experiences the force, and E and B are the fields in the frame S. And very important here is, of course, that this is a local equation. That is, the force is the force that the particle feels at the time R and at the time T at the position R. And the electric field is evaluated at that position at that time. The velocity of the particle is evaluated at that position at that time, because the particle is experiencing an electric force which accelerates it, and the magnetic force which turns it, okay, and I evaluate that at that particular moment. So at that particular space-time point where E and B are, that's where the particle is, and it experiences the force there. I make a big to-do about this, okay, because the locality of these equations will be more and more important as we proceed. The B is evaluated at the position of the particle Q2. Well, in this case, I've written it as particle of charge Q. That's fine. Okay, but now we want, if this is going to be a real equation of relativity, then this equation will have to be true in every frame. Okay, and so if F is this in one frame, then F is going to have to be this in the frame S prime, where I've just decorated it with primes. Well, but then that's a non-trivial expression, because F has to be a force and has to be related to F prime by a Lorentz transformation. But I know how all the things in here transform under Lorentz transformations. I know how the charge transforms. It's invariant under the Lorentz transformation. Okay, charges are Lorentz invariant, as we discuss in detail in the book, and discuss the experimental evidence for that. Okay, and then I know how U transforms to U prime, and I'm going to therefore learn how E and B transform from one frame to the other in such a way that this equation is covariant. Okay, so let's do the exercise. It's interesting to do the exercise and get the relationship. We'll learn quite a lot from doing this. It's easy as well. Okay, so we know how F transforms. Here's F prime in general, given in terms of F and U. I'm just recording the transformation law that we derived a few lectures ago. Okay, I've written it down for F sub x prime, and I've written it down for F prime dot U prime, because those are the two bits of it that I'm going to emphasize in the first part of this discussion. But you can look back in your equations and your discussion and see what happens in the transverse directions as well. Okay, so to understand how the force in the direction of the boost transforms, that involves me with the force in the x direction in the other frame, but it also involves me, okay, with the force in the other directions, because F dot U comes into this formula. Well, F dot U, let's try to simplify that a little bit. We know that F satisfies the Lorentz force law, And so it's given by q parentheses e plus u cross b. So I can take f dot u and see how it simplifies for that case. And so I do that here. I have two terms, q e dotted into u. Well, that's whatever it is. Nothing much I can do with it. And then in the second term, I have q u cross b dotted into u. But that's u cross b. That's taking the cross product. The cross product is perpendicular to the two vectors that formed it. So it's perpendicular to u, and so that dot product is 0. So so f dot u, the power, is determined only by the electric field, and it's just q times e times dot u. Not an unexpected result. You've seen that sort of thing before in studies of power, perhaps in your mechanics in first and second year of physics. Okay, fine. So collecting everything, I can simplify f dot u up here and just replace it by q times e dot u. Okay, and then I can just write down f prime in terms of f applying the Lorentz transformation. So f prime sub x is related to f in the x direction. F in the x direction is we'll just take the Lorentz force law and project it in the x direction. So it's q e in the x direction plus u cross b in the x direction. Okay, and then and then in this I also have a second term in the numerator, minus v over c squared f dot u, and then here's f dot u written down. And then I have the denominator of a form that we've been familiar with. We learned about it in relativity of simultaneity, and I've written it down here. Okay, so nothing mysterious there. I just plug it in. Okay. But now you see this formula is going to determine e primes in terms of e and b, and b prime in terms of e and b. Okay, so let's write it out. Okay, so the left-hand side is well, I can cancel q from both sides of the equation everywhere, and so I have e prime sub x plus the second term. Okay, I know how u prime transforms from one frame to the other. We did that in the past section in part 1 of lecture 3. Okay, and there were simple transformation laws that applied there. I can just go back to my equations for the addition of velocities. Okay, the addition of velocities between different frames, and I'll write them down in a perfectly general case. Okay, in this particular situation, instead of just having u in the y direction like I had in part 1 of this lecture series, I might have that u points in with components in the x, y, and z directions. And so I go back to my full equations for the transformation law of velocities between the frame s and s prime, and I plug in there. So when I do that, I get these formulas. In particular, u prime cross b in the x direction. Well, that's going to involve u prime in the y direction times b prime in the z direction minus u prime in the z direction times b prime in the y direction. Just doing the cross product here of u prime cross b prime. And then I'll take my expressions for u prime in the y direction and u prime in the z direction and look back at the transformation law to get how they're related to u in the y direction and u in the z direction. And that's what I've done in this formula. I've just written it down. I just pulled it out and written it down like that. Nothing mysterious about that. Just applying what I know about how to add velocities in special relativity. That takes care of my left-hand side. And my right-hand side, I want to simplify it a little bit. Okay, so I see e sub x over here. Okay, and I see u cross b in the x direction. Okay, u cross b in the x direction, that's uy bz minus uz by, just taking the cross product. okay? And then I have V over C squared and then E dot U, okay? So I have E dot U, and so I have EX times UX plus EY times UY, okay, plus EZ plus UZ, okay? Just writing out the dot product for a general U in Cartesian coordinates. And that's all I've done here. That's all I've done here. Okay. In the case of the components in the x direction, that was, I got there E sub x times U sub x. Okay. And so I take that term and combine it with the E sub x over here. Okay. And then I check that the factor that multiplies E sub x cancels the denominator, and I guess get E sub x over here. So I've done a little bit of algebra along the way, and you should simply check me because it's just algebra. There's no mystery about that. I've just plugged things in. No real skill there. Just following our noses. Okay, so then this left-hand side has to be the right-hand side. Okay, and how can that be the case? It looks like a real mess. But now think about it. The velocity u is completely arbitrary. E sub x, E sub y, and E sub z. I mean, u sub x, u sub y, and u sub z. The velocity of the particle q in the frame S, or whatever you want. This has to be true for all cases of u. Okay, and so if it's going to be true for all cases of u, okay, then the coefficient of u sub y on the left has to match the coefficient of u sub y on the right. This term and this term. The coefficient of u sub z on the left has to match the coefficient of u sub z on the right. Aha, that really takes it apart. So actually hiding here are three equations. Okay? And so I just match coefficients left and right. Well, the first part is easy. E sub x prime is equal to E sub x. Okay, so the electric field in the direction of the boost is unaffected by the boost. Okay, that's a simple transformation law. But then I see the others are a little bit more intricate. I can isolate the terms in which are proportional to u sub z. That's this term. Okay, u sub z. That's this term. U sub z. That's this term. Match them on both sides, and I see that b sub y prime is equal to gamma times parentheses b sub y plus v over c squared e sub z. Right? You see that? You see that? Okay. So u sub y here isolates b prime sub y. That's what I got here. And then u sub z on this side isolates b sub y. That's this term. It isolates this term e sub z. Okay. Okay, which comes in with a prefactor of v over c squared, and that's what I've written down there. And then similarly for bz sub prime is also related. This matches the coefficients to the other equation. So to get the equations to work for all velocities u, I deduce three equalities that must be true, and that tells me how the electric field and magnetic field transforms from one frame to the other. So that gives me a bit of it, and then I have to look at the y component of the force and do similar algebra. So I concentrated on the x component of the Lorentz force law, requiring that the Lorentz force law be covariant, and I have to check that it's true for the y component and the z component as well. And that's done in the textbook, similar algebra, no new ideas. And then I'll read off that the magnetic field in the direction of the boost is invariant to the boost. And then I'll read off how E sub y transforms and E sub z transforms under the boost. Okay. Well, this is an important result. I learned that all components of E and B mix. right? Look at the formulas here. Everything mixes with everything else, okay? Electric effects in one frame are therefore magnetic in another. Okay, I change frames, and you see E sub z contributes to the magnetic field in the frame S prime. Okay, B sub y contributes to the electric field in the frame S prime. So just like space and time were mixing in Lorentz transformations, the different components of the electric field mix when I make a Lorentz transformation. In fact, in order to transform any particular component of the electric field or the magnetic field between frames, okay, and let's imagine boosts in the x, y, and z direction, then I'll have to know the electric and magnetic fields in the other frame in all the directions to get the electric field or the magnetic field in one direction in the lab frame. So that all of the E's and B's mix, and so I refer that therefore to the electromagnetic field as being all 6 components of E and B. Okay? Okay, that's critical. We now learn that contrary to the ideas of Newton, that the electric field describes everything, we have to have all 3 components of the electric field and all 3 of the components of the magnetic field to describe electromagnetic phenomena, right? Because if I change frames, all these components mix up according to these transformation laws. Well, these are new transformation laws. They involve 6 components. I'm sort of happy where we stood with the transformation laws for the time and space that involve 4 components. And so I really have to do some work to understand how a 6-component object, the electromagnetic field, transforms according to Boost, and that's a subject that we're going to spend some time on as we move forward in this course. Okay, so I want to end this discussion with a little bit more about invariants and 4 vectors. It's clear now that we have to get a little more sophisticated with our formalism, okay, to accommodate the various transformation laws for the new fields and vectors and tensors that we discovered. Okay, so I'll spend just a moment on that here. Okay, more on invariants and 4 vectors in special relativity. Remember, 4 vectors make it easier to write covariant equations. 4 vectors just transform under Lorentz transformations and always in the same way, right? X, the 4 vector x mu, which consists of t and the vector x, transformed in the same way as the energy momentum 4 vector E and P. Okay, and we've seen that. And we can imagine a general 4 vector transforming in the same way. Once we know how they transform, we know how to make invariants, and we know that, and we know how to write down equations which will then have the same structure in any frame. We know how to write covariant expressions as soon as we identify 4 vectors. Okay, so we should try to search for 4 vectors. That's where the simplicity is in relativity. So we might say, let's find a 4 velocity. Well, how would you make such a 4 velocity? Well, the natural thing is to make a 4 vector u upper mu goes from 0 to 3, is equal to dx mu by d tau, right? In that case, you see that u upper mu has the same transformation law as x upper mu. That's a 4 vector. This isn't the 3 vector velocity, right? That was dx vector dt. This is dx mu d tau, right? We want d tau here down here because d tau, the invariant interval, the proper time, okay, is Lorentz invariant. So I can see all the transformation properties coming from x mu, and therefore u mu inherits that. And remember that d tau, the proper time, that's the time on the clock carried by the particle that's moving, is related to the time in the lab frame by a factor of gamma of the speed of the particle, like this. That's just a statement of time dilation. And the proper time, of course, is Lorentz invariant. Right? The proper time means I jump onto the particle, and that's where I measure time. Okay? Okay. So it's very specific to that particular situation. By definition, it's an invariant, and we can write it explicitly as an invariant, and we've done so. Okay, and we'll do more of that as we proceed. So okay, so d tau refers to the invariant time in the instantaneous rest frame of the particle, which is moving instantaneously at the velocity u. Okay, so this fellow there is a 4 vector, and remember that d tau is related to dt by a factor of gamma based on the velocity of the particle, and this statement is just time dilation. Okay, an observer at rest in S has a clock that measures dt, and it's related to the clock measurements on the particle that has velocity u by a factor of gamma, and that's time dilation. So nothing new, but the formalism is a little more general and a little bit more sophisticated. Okay, so now I can take a look at the formula for u upper mu as d by d tau and x mu. X mu, I know, is the 4 vector of t and x, and so I can take d by d tau of it, and that's what I've written down here. x0 is ct. x1, x2, x3 is just the components of the position x, y, z. So I've written it down here as x with a tilde under it to indicate a vector, and they're differentiated with respect to tau. Okay, so I have dt by d tau. Dt by d tau, well, I know what that is. That's just gamma. And I can write, instead of doing dx by d tau, I can do dx by dt, and then dt by d tau by the chain rule. I can pull out a factor of dt by d tau, like this, and dp by d tau is gamma. Okay, so at the end of the day, I see that the 4 vector velocity is gamma times a 4 vector, the first component of which is c, speed of light, speed limit, and the other components are just the ordinary velocity that I'm so familiar with. Okay, but you see now, that's very useful, because this side of the equation transforms by Lorentz transformations, and so if I write that Lorentz transformation out, then I infer what the Lorentz transformation is for the ordinary velocity, okay, appropriately. So it's another way to derive the addition of velocities in relativity. Just write that out. And I leave that to you, and we'll discuss that in recitation section as exercise to understand the formulas. Now we can take a look at the length of this 4 vector. By that I write u squared, and I mean by that u dot u. Okay, so I mean to take the dot product of the components of the 4 vector, and the dot product is defined by the metric and Minkowski space, which is to take the time component, square it, and take minus the dot product of the spatial components, right? And that's what I've written down here. U squared is equal to the square of the time component, that's gamma squared c squared, minus, okay, the magnitude of the 3 vector, which involves a gamma and a u, and I've written that down here. Okay, so I can do some algebra here and isolate c squared minus u squared and write down what gamma squared is, and I see that the whole thing reduces down to c squared. Okay, so that as expected, the length squared of the 4 vector is an invariant. Has to be, we proved that already, and in this case the invariant is c squared. Okay, great. Now an easier way to do that calculation is say, well, I'm taking the length of a 4 vector, so I can do that in any frame because the length of a 4 vector is Lorentz invariant. So let's go to the rest frame of that 4 vector. Well, in the rest frame of the 4 vector velocity has only one component, the 0th component, and that's c. Well, the length of a 4 vector whose only non-zero component is c, and that's the 0th component, is c squared. Voila, right? That's the answer. I don't have to do all this stuff. I can just think it. Okay, just go use the fact that the dot product is invariant and choose the frame in which it's the easiest to evaluate. That's the power of invariant methods, right? And when you did collisions a couple of recitations ago, you used invariance a lot to take advantage of that fact. And we made a lot of progress in very complicated collisions by using that trick. Okay, that's a 4 velocity. I can move on and make a 4 acceleration. Okay, I'll make a 4 acceleration just as the tau derivative of the 4 velocity. What else would you do? Okay, again, since the 4 velocity satisfies the Lorentz transformation, the 4 acceleration inherits that. And then I can do the algebra that I did up here, replace d by d tau by gamma d by dt. Okay, apply that to the 4 velocity, take the derivatives, okay, and get this expression for the 4 velocity. Well, I see that therefore the 4 velocity has components, okay, which involve the velocity itself and the acceleration itself in a particular frame. So again, okay, I can use this fact, write down the Lorentz transformation for the 4 acceleration, the 4 component acceleration, a mu as defined here, and infer the transformation law for its various components, like the 3 acceleration that's lying here. So it gives me an alternative way of making the derivation that was kind of ugly for the 3 acceleration. The 3 acceleration, by that I mean the time rate of change of the 3 velocity, the thing that I'm used to from Newtonian physics. Now I can check that this 4 acceleration is particularly simple in the instantaneous rest frame of the particle, where instantaneously its velocity is 0, so its gamma factor is 1, and if the rate of change of the gamma factor is 0, you can check that. Just take the derivative of gamma with respect to t and see that it's proportional to u dot the acceleration and the velocity is 0 in the instantaneous rest frame, and so this d gamma dt is equal to 0. Okay, so there's a little calculation there that's necessary to show that, and that's how it goes. Okay, so in the instantaneous rest frame, the acceleration, the 4 acceleration, reduces down to the gamma dt's go away, the gamma goes to 1. Okay, it just reduces down to a 4 component object whose components are in the t component 0, and in the xyz direction is just the ordinary acceleration. Okay, well that's handy because now I can ask the question, well, what's the dot product between the two 4 vectors u and a? Well, that's an invariant. Go to the rest frame, the instantaneous rest frame of the particle to evaluate it. That's easy. In the instantaneous rest frame, u has only a non-zero component in the t direction, it's c. In the instantaneous rest frame, a has a non-zero component, and that's a, and it's only in the x, y, and z direction. So the dot product, the invariant dot product, is equal to 0. And we'll use that fact in various problem sets. Okay. Probably the most important observation is that we can also make a 4 force. Okay, so instead of considering d by dt of the momentum, we might consider d by d tau of the 4 momentum p mu, and that's written down here. And I take the derivative here, similar to what I've done up here, so I'll just move along, okay? And I'll see that the 4 force has a component as gamma times a zeroth component, which goes like the three component force dotted into the three velocity, and the x, y, and z components are the ordinary force as well. And so that's interesting, because we discovered when we were considering how forces transform from one frame to another, we had the surprise that the force is mixed with the power F dot u, and here we see why that's the case, because F dot u is actually one of the components of the 4 force, and the 4 force satisfies simple transformation laws, just the Lorentz transformation law. And so I can reproduce my transformation law for the 3 force, okay, by using this approach, and I see that I'm going to get involved in F dot u, the power inextricably. Okay. Now we see why F mixes with F dot u without underboost. Okay. So we'll discuss these more in the problem sets. Okay, and get used to them. We want to identify 4 vectors, because 4 vector relationships are frame independent. They tell us what's covariant, and of course covariance means that they're real physical equations of a physical significance. They're true in any frame, in any coordination of space-time, and that's a step in the right direction. Okay, so I think we'll stop at this point, and then in lecture 8 we'll continue with our study of the electromagnetic